Dark matter has been around since the dawn of time. For 13.8 billion years, dark matter has played a large role in the formation of the universe, and yet scientists still cannot prove its existence. Today I'm going to talk to you about this form of matter that has trumped scientists for around a century. Anything involving space has always interested me, and after taking multiple astronomy classes, dark matter specifically piqued my interest. Dark matter is a theorized form of matter that exists throughout the universe but is difficult to detect physically. Researchers have spent many years attempting many different methods to detect dark matter. Today I'm going to tell you about some of those methods and some of those findings. I'll begin by giving you a brief overview of what dark matter truly is, and then we will focus on the research done to detect dark matter using electron oscillations as well as the Large Hadron Collider. Let's first talk about what I mean when I say dark matter. Dark matter is an undetectable form of matter that only interacts with physical particles through gravity. Its existence is inferred through these gravitational effects on visible matter. It was identified in 1933 by Jan Hendrik Oort and Fritz Zwicky. Alexander Antonov, in his paper Discovery of Dark Space, specifically states, total mass energy of dark matter and dark energy more than 20 times exceeded the mass energy of our visible universe. This means that there is a form of matter out there that we simply cannot see. Scientists have proposed different candidates for dark matter. These theoretical candidates are called cold dark matter and dark photon dark matter. Cold dark matter consists of weakly interacting massive particles, nicknamed WIMPs, that interact with physical matter through gravity. Dark photon dark matter, however, interacts with physical particles through kinetic mixing. So now that you know what dark matter is and why it's so difficult to detect, let's talk about how scientists tried to detect it using the Large Hadron Collider. Scientists investigating cold dark matter believe WIMPs are a viable candidate for dark matter. Using Switzerland's Large Hadron Collider, they aimed to produce dark matter and then detect its effects on standard model particles to search for these WIMPs. According to S.Y. Ho, the main researcher for the paper Dark Matter Searches at the Large Hadron Collider, the presence of WIMPs pair is inferred from missing transverse energy. These scientists believed that slamming two protons into each other at 99.999% the speed of light would result in a detectable recoil against these visible particles in the detector. No missing transverse energy was detected, meaning that they did not detect dark matter. The scientists used this study to refine their ideas about dark matter, narrowing the range for their search. After many studies like this that failed to detect dark matter, technology has improved and has allowed us to detect dark matter through different means, like electron oscillations. Scientists investigating dark photon dark matter believe that dark photons would interact with standard model particles through kinetic mixing. Haipeng An, the main researcher for the study Direct Detection of Dark Photon Dark Matter using the radio telescopes, wrote, the local dark photon dark matter can induce harmonic oscillations of electrons inside the antenna of radio telescopes. The study conducted used the FAST telescope in China to scan the 1 to 1.5 gigahertz frequency range to look for electron oscillations in these radio telescope antennas. The study concluded that there was no dark photon dark matter detected. The studies then theorized that frequency range changes could detect electron oscillations. Haipeng An then suggested that the most powerful telescope, called the James Webb Space Telescope, also known as the JWST, could search for electron oscillations. Earlier this year, An performed this study using the JWST and scanned for oscillations using a much broader range of 10 to 500 terahertz. This again resulted in finding no electron oscillations. An believes that the JWST could still be the answer to detecting dark matter. In his paper, Direct Detection of Dark Photon Dark Matter with the James Webb Space Telescope, we show that by rearranging the positions of reflectors, JWST can achieve a sensitivity stronger than its existing limits by 1 or 2 orders of magnitude. While these studies performed by Haipeng An and his team were not successful in detecting dark matter, the scientists still believe that it is possible and plan to keep trying in the future. In conclusion, researchers have dedicated many years and used various methods to detect dark photon dark matter and cold dark matter, such as searching for electron oscillations in radio telescopes and utilizing the Large Hadron Collider to investigate missing transverse energy. Research for almost an entire century, dark matter still evades science to this day. While the weakly interactive massive particles and dark photon dark matter theories are still the most prominent theories, the research done to detect them has all come back empty. Yet scientists are still not giving up. The mysteries as to how the universe works has always intrigued me, and now that you all know a little more about dark matter, I hope it intrigues you too. Thank you very much for your time.